Right, in this figure, we will now show an overall relationship between the continuous time Fourier series and continuous time Fourier transform. On the top figure, we have x of t, periodic rectangular wave with period t0 and with on period from minus ta to plus ta and amplitude of 1. In the bottom of the figure, we have actually the same single period, but now the signal is aperiodic, where time stretches from minus ta to minus infinity and plus ta to plus infinity with 0 values. So only a single period of x of t exists. There is a very deep relationship between the Fourier transform of this periodic signal versus the aperiodic counterpart. Let us now focus only on the top figure. As we know, we can perform Fourier series or Fourier transform representation of x of t periodic. In the Fourier series representation, we first calculate C0 using this equation, and we have seen in previous example how we have calculated the rectangular pulse Fourier transform Fourier series. C0 is equal to 2Ta divided by T0 in this example, and the rest of the Ck values from minus 1 to minus infinity and k equals to 1 to k equals to infinity is given by this equation. 1 over k pi multiplied by sine k times Ta times omega naught. We then are able to draw the frequency spectrum of Ck, where the x-axis now is k and the y-axis is the values of Ck. Most examples, Ck's are imaginary. However, in this example, because we are even functions, resultant Ck's is a real functions with some positive values of Ck and negative values of Ck. And the phase now for positive value can be considered as 0, and the negative value can be considered as minus pi or pi. When we plot the values of Ck along k, we have the sinc function. What is important is to interpret what is k. K here is just a shorthand notation for the frequency k times omega naught. So along the intervals, we see that for a Fourier series, we only need frequencies at k omega naught and nowhere else in between. From 0 to 1 k omega naught or from 1 to 2 k omega naught, we do not need this frequency. What about the continuous time Fourier transform? Continuous time Fourier transform in this equation clearly shows that omega, the frequencies required, is a continuum. In this case, how can we reconcile the fact that Fourier series has told us that we are only requiring the frequencies at the k omega naught harmonics? The answer now appears that we are using the direct delta functions firing at positions of frequency 0, 1 omega naught, 2 omega naught, 3 omega naught, as well as minus 1 omega naught, minus 2 omega naught, and so on, to reconstruct. The deltas allow us to use the equation in the synthesis equation to reconstruct x of t properly. We now see that there is a slight difference between xj omega and ck's. The reason being that the synthesis equations are different. In the synthesis equation of continuous time Fourier transform, there is a 1 over 2 pi factor in the front of the synthesis equation, while there is none in the synthesis equation for continuous time Fourier series. Hence, the values of Ck's related to CTFT is that it should be multiplied by 2 pi Ck, so that the constant of integration 1 over 2 pi in the synthesis equation is removed. in addition to that, to make xj omega correct in the continuous frequency domain, the delta at omega minus k omega naught is put into the expression for xj omega. Comparing these two figures, ck's and xj omega, in fact, one would think that they are completely the same. So let's recollect what is the difference. The first difference is the amplitude is multiplied by 2 pi with respect to ck. And the second difference is that in the continuous time Fourier transform representation omega, the deltas are being used at position of k multiplied by omega naught. The values associated with each delta is 2 pi multiplied by ck at the position of delta omega minus k omega naught. We now turn our attention to the continuous time Fourier transform of a single period of the periodic signal. We think that there is a deep difference. Let us now first plot the continuous time Fourier transform. It looks like this, the sinc function. If we study this more closely, we realize two things. One is that the values of ck, it's 1 over t naught of xj omega. In other words, we can also think that ck times t naught is equals to xj omega, where xj omega is the continuous time Fourier transform of a single period. So this is the relationship. We will derive this relationship later, but now in this figure, we have an overall picture of what is the difference between continuous time Fourier series Fourier transform of a periodic signal versus the continuous time Fourier transform of a single period of the periodic signal. Right, let us continue the CTFT and CTFS relationship. In particular, I'm going to again examine the periodic signal and see why the deltas are being used in xj omega. We know that if the signal can be represented as a Fourier series, it looks like this. Where k equals to minus infinity to infinity, and ck's are the Fourier series coefficient. This basically is the synthesis equation of the continuous time Fourier series. Now, if the above is true, and for this to be true, x of t must satisfy some Dirichlet conditions, then the left-hand side will be equals to the right-hand side in some mean square sense. We now will apply x of j omega, or we are going to apply the continuous time Fourier transform using the representation of xt in this form. Basically, we first write the continuous time Fourier transform equation, the analysis equation, which is integral from minus infinity to infinity, and we place x of t here with the representation on top. We have not changed any equations at all. This remains the analysis equation, except being applied to this representation. We can move the integral or switch the integral and the summation in this form. The theory is beyond the scope of this work, but let us proceed to manipulate. When we have reached this form, the interesting equation is the red box on the right hand side. And this can be reduced to two pi delta omega minus k omega naught. And hence we have arrived in we see that the continuous time Fourier transform of periodic signal x of t is equals to the continuous time Fourier series coefficient multiplied by 2 pi, where this coefficient ck is standing on deltas at omega equals to k omega naught, for k equals to negative infinity to infinity.